In video 42 on the Foundations of Computational Economics course, we will implement the endogenous gridpoint method for the consumption savings problem. And so this is a practical video where we do hands-on coding again. And the plan is to basically add a new solver to the Deaton's class, the EGM solver, and then we can run more of the accuracy comparisons with VFI, time iterations, and now EGM, and also run the Keynes test. If you remember, that's the test which is based on the theoretical property of the simulated consumption path from the model. And this consumption path has to be completely flat under certain parameterization in the deterministic consumption savings model. So the code that we start from here comes from video 40, and of course previous video 41 has all the theory on EGM. So let me go to the standard notebook view and start working with the code. Here's the copy from video 40, and let's run it. Just to remind ourselves, okay, we're solving the consumption savings problem here. Here are the value functions and the policy function. They converge in the time iteration solver, and then with also VFI, two versions of VFI, discrete and discretized and continuous. Okay, that was the this is the solution with income, and you can see that because of this little 45-degree line segment of the policy function where you consume everything. In the k-keating specification, that's not going to be the case, right? The optimal policy starts from the origin. This is just a line, and we can solve it still with many different methods. Now this is a bit annoying. So we're dividing by 0 when solving with time iterations. Let's try to track down this problem. And I already did some testing, and it's coming here in the early residual when we're calling the marginal utility function, which is 1 over c, right, for log utility. And so if c1 is very close to 0, then this error is triggered right here. So to counteract that, we can make sure that this c1 is never very close to 0. And to do that, it's fairly simple. Self grid 0 contains the little epsilon in this model. And this trick we've done many times already. Okay, just to check that we don't get this annoying warning. Yeah, I think it's fine. Okay, so let's implement the EGM solver. Remember, EGM is pretty much the same as time iteration, but with a Kalman Refit operator implemented in a much better way. So I'm going to start by copying the solve time eater method and renaming that to solve EGM. The parameters are going to be, the arguments are going to be the same, using EGM. EGM, which is successive approximation of efficient Kalman Refit. Yeah, that's right. All right, and so where do we start? Let me open the notes 41, the notebook 41, and here we will have the EGM algorithm written out. Okay, set a grid on post-decision state A instead of state M. Let's just do that. It's going to be lean space. So A can be exactly 0, actually, right? Because exactly 0 savings means that we are exactly at the corner, at the point where the corner solution and the interior solution touch. And so 0 is important. Now self, what's the maximum? M bar can be our upper bound. And let's do the same number of grid points as state points. Doesn't really matter. Okay, now the initial policy defined over 2 points. Okay, so to do that, so we don't need self-grid anymore. And moreover, we are going to be working with exact zeros here at AGM. And it's important to use linear interpolation to be able to capture the corner solutions accurately. Okay, right. And because the grids are going to be changing all the time as we go through the iterations, then it's actually more convenient to pass around not the vector of values of the policy function, but instead the interpolation function for the policy function itself. And that means that we can create the policy function, the initial one, as the interpolation function right away. And I'm scrolling up to copy the interpolation function that would be given here. And remember, we need to use linear interpolation for EGM for it to work correctly, at least in this constraint region. We could use a different scheme for the other points, but then it's a combination which is possible, but it's a bit messy to implement. So I'll leave it for your own work. Okay, and so we're going to be interpolating the 45-degree line, which is simply, 0 m bar and 0 m bar again. This is our initial policy. Now, with value function, I didn't say anything in the previous video about the value function and how to calculate value function with EGM. The answer is that it's possible to do alone with EGM, and because the time iterations, they also work in the policy function space, then we can use exactly same ways that the value function is calculated. So I'm going to use the same code essentially for the value function as I modify this script or this code. Okay. Now, allocating space for the policy and value function. We'll have to do that. Interpolation function for the policy. And see here, we are already using C0 as the interpolation policy. So C0 is already interpolated. Okay, here's where here we start deviating, right? And that's because we're not using a grid over the state space, and so we cannot loop over the points of the state space anymore. But then afterwards, we actually do have to calculate the difference between the policy functions and the callback and the error. Okay, and prepare for the next iteration. Self-solution in return. All right, so we'll have to do a little bit more of the a little bit more to deal with the endogenous grid points over the state space, because the rest of the code is written to work with the fixed grid over the state space. Okay, well, we'll have to live with that. I mean, it would be more efficient to write just the EGM solver and everything else in the class to work with the endogenous grid points, but that's not how it's done here. So we'll deal with that. Okay, so what's the next step to do in the EGM solver? Increment the iteration counter. For each point of the grid, perform the EGM step. Okay, well, we're not going to do an EGM step for each point of the grid. Of course, we will vectorize this code. So we'll do EGM step for all of the points on A. let me say EGM step here. And how do we do EGM step? Well, actually, the code is right here. It's almost the same as calculating the early residual. So let me actually copy all of this into the section with EGM step. And look, M1 is going to be the self next period wealth of M0, C0, and Y. Sorry, these are the inputs into the early residual calculator. Right, but so what's the idea here? The idea, we're going to be working with this instance where with the case where C is NP array. Well, we need to work on A, but still. So the idea is that that C and M are along axis 0, and the quadrature points are along axis 1. And then we call the next period wealth. All right, let's do that directly in the EGM solver. So I'm going to replace Y with quadrature points. Let's say matrix with A in axis 0, Y quad points in axis 1. And that's what I want. Now A should go instead of M. Can the next period still work with that? Where's my next period wealth? There. If C is just 0, then M minus C is just calculated as M minus C. So if I give A instead of M and 0 instead of C, then we get what we need. Okay, but A needs to be column vector, right? So let's add a new dimension here to A. Vector of savings. Something is happening here. Okay, so now A and just 0. Okay, we'll correctly calculate the next period wealth as a matrix. Why is that? Well, that's because A as savings is going to be in a column vector, and it's going to replace M minus C because C is 0, and this is going to replace the quadrature points. Okay, good. Now C is going to be, again, the maximum between policy M1. Well, policy is actually C naught, right? Because C naught is already the interpolation function that returns the correct consumption. And then yeah, we contrast that with 0 or yes. And then marginal utility is calculated of C1, and that's still correct. We're calculating this part here. So we've calculated the optimal consumption of array plus Y, now the marginal utility, and then we have to take the expectation. So marginal utility is here, and then we have to take the expectation, EMU, expected marginal utility. Self beta R, actually let me just keep calling it right-hand side. That's the right-hand side of the early equation. NP dot mu times the quadrature weights. So exactly the same way as we did in the early residual calculator. But here comes the difference, right? Now C is going to be given by the marginal utility inverse of the right-hand side. So let me say inverse marginal utility of the right-hand side. And we need to code this one up. And let's go back to where the utility functions are. Well, for log, it's just the same thing, right? But let me kind of make u as a variable there. For other utility functions, they might be different, so let's have them separate like that. So I want self inverse marginal utility of right-hand side. Current period consumption as a vector, right? And now M will be C plus A. And this is also a vector. Endogenous points on M. Okay, now so this and this are now the points that I described in this transformation. We've calculated the C primes, and the C primes with A gives us the M's. And see, now we can just say that the policy function C1 is just the interpolation of the endogenous points M, called just M, and the calculated C's. And you know what, let me, because we're going to call this 2 times already, let me create the lambda function for x and f, which is just the interpolation routine. Okay, so this is going to be the local interpolation function. Oh, the local interpolation routine that returns the interpolation function. Okay, now I can call that with M and C. And this will be the updated policy function. So we've done everything that was done here for each point of the state space. And what's left is the calculation of the value function for given M and found optimal consumption function C1, which is now a function. Okay, so this is the interpolation of the value function from the previous value, and we can leave it like that, so the interpolation of the value function can be controlled from the outside. M1 is now self next period wealth of M. Okay, here comes C1, but this is C1 of I. I see. So maybe I've done something too fast. Where does I come from? Calculation of the value function can be done point by point. That's, or at least that's how it was done here. Oh, can we do better? Yeah, I think we can do better. So interpolation function, we basically have to copy the Bellman equation, right? The Bellman equation for which the policy function is already known. It's this one. So let's see. if we copy this part, self next period MC, C is going to be given, M is going to be just the grid, and we need to calculate the expectation correctly. So M should be in the first column, in the column. Let's see if this helps us. Well, it's pretty much the same thing, right? The interpolation, interfunc. So I want to understand where this M is coming from. Right now, M is the endogenous grid. This is definitely not what we wanted. So let's redo M, self grid. But we want it to be the column vector. And so a self M1, self next period M, and now I want to do the interpolation of the policy function C1, the updated one, on this normal state grid M, and with cell quadrature points. In the second axis. Okay, and this is again matrix. Next period wealth, matrix of next period wealth with states in axis 0, quad points, axis 1. Okay, now we can calculate the value in those points M1, and then we can calculate the expectation of that value here. Value function in the next period wealth, expected value function scalar. Well, it's not scalar, it's a vector. Now it's a vector because we calculated the matrix. Okay, and now V1 is going to be the self-utility of C1. Okay, well, let's do the C, recalculate C over here just once. It's normal state grid. And this is consumption. On normal state grid. Okay. So now we can use consumption here. I have to be careful with the shapes now. So this is C state grid column vector, and this is also a column vector. Utility of C, that's a C1, and self beta EV. So this is the maximand of the Bellman equation. It's not scalar, it's a vector. And which vector? So we took the, this is a column vector as well, right? Right, this is a column vector, but this is for all the states. So I wonder if I can actually do so for the dot product, can I lose a dimension there? NumPy dot. Yeah. Is there a parameter saying preserve dimension or something like that? This must be exact kind of output argument. So that's where it would put the result. Don't see anything about preserving dimensions. Okay. Let's just try that and debug later. So we've done all of this. Now, what we have in V1 is the actual value defined on the state grid, but maybe it's in the wrong dimension. Okay. Now we want to check convergence in the policy function space, but see, C1 is the interpolation function, so as C0. So what we do want, we want the to calculate them at some points, and maybe those points can be the points of the state space itself, like that. So C1 is the interpolation function and C0 is an interpolation function, and so let's compare their interpolated values in the same points of the state space. I want to put some comment there to mark the section where we're calculating the value function. Okay, the callback is policy should be C1 again of the state space. Let's say C1 on state grid, on grid. And actually it's right there, isn't it right, but different dimension. Okay, let's keep it separate. And C0 on grid. We want C1 on grid here. Policy value. Prepare for the next iteration. So C0 is now going to be the C1. That's right. This is right. And when we return, we want to give it C1 grid to make it compatible with everything else. Okay, I think we are ready to start checking, and let me use this formulation here and comment everything out and say M solve EGM. What kind of bugs do we get? The X-array must be exactly one dimension. Where's this coming from? Solve EGM, C1, interp, M, and C. Updated policy function. XF, X and F. Oh, this is strange. This is unexpected. So we're using the interpolation in 1D of X and F. And this is firing not here. Is it? But where we have C1. Right, and this, so A is a column vector of savings, and this is not good. Let's just make it a grid on savings. And when we pass it to the wealth calculator, that's when we make it a column vector and a column. Okay, and this should be better. Oh, and we got some answers. Interesting. So let's look at them in the visualization, which is much easier for debugging. So I'm gonna say that there's gonna be another solver, EGM, and then we'll just solve EGM, see how extendable this code is. And we want to plot, solve plot with EGM. Let's see what we get. Lots of iterations, and it's not particularly fast. Something's going on. Whew. Very different, isn't it? Guess Bellman continues. Well, let's keep it. So it's very far from what we are supposed to get. Yeah, especially here. So the policy function went up. That's interesting. This is the initial one. Oh, yeah, I think we forgot this additional point, didn't we? So C1 should be an empty of one with one more point. And then M1, C1 is the maximum of C0 of M. So C1, and actually this doesn't include V. V should be just fine. C0 no, wait a second. So what's going on here? C1 is just the interpolation. Yeah. Okay. So here C and M should have an additional point. So here C should be allocated space with one additional point, and M, same thing. And now C of 0, same as M of 0, should be just zeros, and C of 1 to the end like so. Let's try it again. Oh, it's taken a lot of iterations still. But it produced something similar, didn't it? Well, -2 to 5. No, the value function is off, and the policy function is quite sensible, actually. So what's going on here? Well, judging by the fact that this is really black, so it's like it's doing a lot more iterations on the value function space, it seems, but the convergence on the policy function is pretty much the same. That tells me that we're plotting a lot more value functions for some reason, and the reason is probably that we are messing up the dimensions of these objects here that we used to calculate the value function. Right, it's here. And so probably it's just because that M is column vector, C is a column vector. Interpolation, next period, wealth is a matrix, right, with states on the vertical axis and on axis x equals 0 and quadrature points on the axis equals 1. Now the dot product produces the flat interpolation, then the dot product produces the flat one-dimensional array. But here the utility of C is actually producing a vector, a column vector again. And so this becomes a matrix. V1 is a matrix. And that's probably why we're seeing lots of lines over there that we don't need. So let's go through this again. Well, actually we don't need to allocate space to V1 because we're just using, we are assigning this whole vector. So this only makes sense if we're computing V1 point by point. All right. Everything seems to be good here. But look, we will need to compute the grid. We will need to compute the policy function on the grid. So why don't we move this whole line up here, and we will have the vector representation of policy function. And then start from here. So let me comment out these two. We want to compute M1 as a matrix. And that's true. But let's do it all in place. So self-grid is going to give us the grid space, the grid over the state space. And we want it to be a column. Then here we can put C1 grid right away. This is the updated consumption, updated policy function represented on the grid. And we want it to be vertical column vector as well. And then the quadrature points should be the row vector. Okay, so this is now a matrix. And we are getting ready to interpolate the value function. Right. And V is now interpolated. The dot product returns a flat array. And here we can calculate using this C1 grid as well. Which because C1 grid is a one-dimensional array, then this utility of that is going to be one-dimensional. This is going to be one-dimensional. So this is all going to be one-dimensional now. And we can get rid of these additional lines. Now, converged or not, we can compare to the C0 on self-grid, and we don't need these two. Now, callback policy is going to get us C1 grid, that's correct, and V1. These are all vector representations for the policy function and the value function. And C1 grid, and the solution is C1 grid as well. Okay, let's try again. Oh, something's wrong here. If callback. Oh, what's wrong? Am I missing a... Yeah, okay. I was missing a bracket. All right, there we are. Okay, so here we're solving with EGM, and then we're solving with time iteration right away. And it actually takes the same number of iterations to converge, it seems, judging by the length of these bars. And that's actually shouldn't be surprising, right? Because we're doing pretty much the same thing. We're doing time iterations with a better Kalman Raffet operator and nothing more. It's just that this is a lot faster. Or it should be at least. Let's check the accuracy on both of these solvers. The accuracy should be similar, if not identical. So 1.49 10 to the minus 5. No, wait, where am I? It's here. 1.9393, 1.90. It's a little bit better even on the time iteration. Well, why is that? That's because, is it because of the interpolation that is not necessarily linear, but I think it is linear for the time iterations as well. That's interesting. It could also be because we are missing some points with EGM. When we are with endogenous grids, we're getting slightly less points between 0 and 10 on the wealth grid, right? Because some of the endogenous grid points are above 10, as we saw in the previous video. So that might be the reason as well. But the real test is timing. Can we run this again? It goes really fast. Well, not so fast. Okay, let's do a proper timing comparison. Let's go, I want to go back to all the way to study of algorithms. Remember, we were timing the code there. It is here somewhere. Right, so time it will time the line and double lines of the code set up. Okay, so let's try to do some timing comparisons. Insert a cell above. Oh, we have to be careful with these replications, because it can take really long time. Let's do 10 by 10 now. 100 times solving the problem could be a bit too much. Let's start with 2 by 2 setup command. We have to create the problem and then solve EGM. We're going to time this. Let's do it. Invalid syntax. Yeah. Okay. Okay, about 10.9 milliseconds. Oh, that was a large error. Let's try to do a more accurate measurement. Yeah, okay, so about a little bit under, well, around 10 milliseconds plus minus half a millisecond. That's for the EGM. And if we do the same thing for time iteration, oh, that was a mistake. We are running 100 solvers, so that'll take some time actually. All right, let's look at the rest of the code in the meanwhile. So what else do we want to do? We want to make measure accuracy, run a simulator here after the model is solved by EGM. Yeah, we have to wait for all of that. Are we interested in this? What's on the plan? So compare accuracy of solution using squared early residuals. Okay, let's do that. For time iterations in VFI, run the Keynes test. So Keynes test is the next really interesting application. Okay, I'm not going to do the solve. I'm just going to do the accuracy test. Instead of solve plot, I'm just going to do solve time iter like this, right? Solver accuracy test. And same thing for VFI. And we have Bellman continuous now. Test, and then Bellman discretized. So with VFI, and do an accuracy as well. So are we done here? No. Still running. Should we wait? Should I kill it? Let's take 10 seconds to think. Well, apparently that was enough. Okay, so 100 runs complete. One run took about 1.25 seconds. So what? It is about 100 times slower than EGM. And remember, we're using the same number of grid points. Right? So, yeah, in the standard error, we've already done it with EGM. Okay, so that's not surprising. EGM is very fast. It avoids root finding operations, but it keeps the accuracy at the same level as time iterations. And let's look at the actual measures of accuracy. You can see that EGM is slightly lower than the time iterations, just a tiny bit, but lower. So why could that be? Well, I'm thinking that we're measuring the accuracy as the squared early residuals over the range of state space, right, between 0 and 10. And time iterations definitely have all the grid points that we asked for there, namely 100. But EGM puts some of the endogenous grid points above 10, above the upper bound. And so apparently it has, inherently it has lower number of points where we are measuring the accuracy. So that's probably why there is slightly less accuracy here. Okay, what about the early residuals continuous Bellman using 1,000 points and at 250, right? I'm sorry, this doesn't apply for the continuous Bellman. So well, it is also not too bad, right? So if we're looking for the optimal consumption in the solving the optimization problem, then the accuracy is comparable. It's not as good as the earlier as the EGM or the time iterations, but it's comparable. And then it's completely way off when we discretize our choice space. By the way, this says that we've solved with time iterations, which is not true. So there is a bug somewhere in naming. So time iter, I guess that's where we're saving the solution. Yeah, here we should say EGM. Just to check that I've changed something. EGM here, yeah. Okay, let's try to solve the key-kitting version with EGM as well. How do we do that? We'll just copy these lines here. And we say instead of time iter, say EGM. Yeah, you can see that EGM just spits out the solution right away. And you can see the quality is pretty high, as also supported by this accuracy measure. The number of iterations is more or less the same. You can see that simulation lines are really smooth and nice. So just as they are here, the accuracy is comparable, isn't it? 1.49 10 to the minus 5 and 1.49 10 to the minus 5. It's just a lot faster than time iterations. Okay, the continuous Bellman has some wiggles here. Yeah, well, we know that for key-kitting problem, even the continuous Bellman has difficulty because of the need to interpolate a really curvy value function. Same thing here. Okay, here's our Keen test. The idea is that if we set beta r equals 1, then from the early equation that we usually have, right, this becomes 1. And now imagine that it's also a deterministic problem. so there's no expectation. So what we end up with is just the equality of the marginal utilities in 2 consecutive periods. Of course, m prime is a function of the c star of m, and that means that if we have a slight inaccuracy in c here, then this m prime is going to be different, and this equality is harder to solve. Of course, it follows that the marginal utilities of consumption of 2 consecutive periods should be the same, and that therefore the levels of consumption should be the same as well. So this we can check really easily in the simulated trajectory. So let's try to do that. And where's my code? Here's some code. So we can have an initial wealth and say 100 time periods. We first set up the model such that beta is 0.9 and r is 1 over 0.9, so the product is 1. We're going to set sigma to a tiny number. We can't really do exactly 0 because of the quadrature that is still there. We could have coded up a special case for sigma equals to 0 and then just keep calculating quadrature altogether. But that's an additional thing. We're going to only use 2 quadrature points because we're not calculating an expectation effectively. So let's not waste time and space for that. VFI, continuous VFI, time iterations. And then there is a plot here, which, well, we're saving simulations under different names. And then we're plotting the simulated consumption path. So as we see, the blue line, which is the VFI with discretized choice, is basically blown out of the water already. It starts too low, it seems, and then has to gain on consumption to catch up with the flat consumption profile, but then overshoots. And time iteration seems to be producing a declining profile, whereas the VFI produces the more flat profile. Okay, well, let's add the new EGM here. And what's the prediction? It should be similar to time iterations, right? We've just seen that the accuracy is the same, where it's just that EGM is so much faster. Let's do that, though. I'll probably take out the discretized VFI right away. Let's run the test again. And again, just to remind you, this is a very hard test. This is the test where tiny mistakes, tiny inaccuracies accumulate in a simulation and produce more and more. Oh, I should have taken this line out as well. We're not recalculating it, but I should have added a new line. Wait a second, this is all wrong. sim2, sim3. We should have sim4 and add the sim4 line and call it EGM line, like this. VFI with continuous choice takes time. It needs more iterations to converge, and then because it solves the optimization problem in every point in the state space, then that's what takes time. The time iteration is a little fast. So the accuracy of solution is actually comparable for all of them, and this is very nice. But now the EGM and time iteration, which is they seem to overlap. They are producing a worse simulation than the VFI with continuous Bellman. Now, what's the difference between these two methods? When we say solve VFI, we converge in the value function space, whereas in the time iteration and EGM, we converge in the policy function space. And the tolerances by the default are the same as far as I remember. Let's see. Yeah, the tolerance of convergence is 10 over to the power of minus 4, so 1 over 10 to the 4th. So this is a real test, right? So let's make tolerances really small for everybody to make sure that we actually get to the point which is the solution, to the fixed point of the corresponding operator. Let's see what we get here. I'm just going to pause the video. And all this waiting just to get the no convergence. Okay, let's try to reduce this to say -8 and also add max iter equals 1000 and start again. It took about a minute before it ran out of iterations. So I'll pause the video again. And we have the results. Look at this. So it took some time, it took minutes to converge. And the accuracy measures are actually comparable. There we are. So the Keynes test is a stronger test. It's more complicated. And time iterations actually produce the most flat profile from what I can see. Can I increase the zoom on this? Well, they are deviating slightly to two directions, the EGM and the time iterations. And what's the error, the magnitude of error here? Well, this is 10 to the -8. And we're looking at, a fraction of a unity. So it's a pretty good accuracy. I would say this is almost flat. Of course, it needs to be just completely flat. But we can get there with more points. We can get down to machine precision with more points on the grid and maybe a lower tolerance here. Okay, let me stop here. This is the endogenous gridpoint method. As I said, the best solution method for the consumption savings problem. It is very, very useful to know. And if you're solving a problem that is solvable by EGM, that's definitely the way to go. See you in the next one.